Okay, you guys, so we are moving on. We are into concept 1.3, okay? And so now we're really looking at what we were just talking about in concept 1.8. I know it seems weird that the order is backwards, but we're making do. So you can see this sort of ongoing process that is the scientific method that begins with thinking of some sort of investigative question, formulating hypotheses based on the observations and background research that you have come up with and found, for then to formulate some predictions that you can then test, perhaps after multiple tests and repeated trials and proving these predictions true in repeated trials, then perhaps we've developed a theory, right? But perhaps at this point of prediction, right, we actually reject our hypothesis. Then, the process starts over. We reformulate a hypothesis, we reformulate our predictions, and so on and so forth. So it's this kind of ongoing process, this cyclic process. Okay, so how do we formulate a hypothesis? Okay, so basically there's two types of reasoning, and one helps us in formulating a hypothesis. One helps us in formulating a prediction for the experiment. So first, we'll talk about inductive reasoning, which is what we'll use to formulate a hypothesis, okay? And inductive reasoning, it comes from lots of different observations. So if we read this, right, members of a species are not all the same. We've observed this. We've observed individuals are competing for resources. We've observed that species are generally adapted to their environment, okay? Then we're able to draw some sort of a conclusion from this background research that we've garnered, okay? So this all of these observations inform you as you formulate your hypothesis. But for us to get it into that if then because format that I'm expecting, right, we actually need to use what is called deductive reasoning, okay, where we're using essentially information that is from a general premise, and we're thinking that will apply to our prediction. So for example, we know of this general premise that individuals that are most adapted to their environment are more likely to pass on their traits to the next generation. Okay, from that premise, we are able to deduce and create this hypothetical statement. Okay, through deductive reasoning, we can formulate our if, then, because formatted prediction. So if the average temperature in an ecosystem increases due to climate change, individuals that are better adapted to warm temperatures will outcompete those that are not. We've used some deductive reasoning to come to this conclusion. Okay, so, moving on. And then let's make sure in our notes where we're at. So one moment. So I'm going to go back a slide here. Okay, so let's have our fill-ins. Okay, so listen closely. So the process of science, the scientific method acts as a guideline for scientific studies. Okay, acts as a guideline. So observations are formal ways of seeing what happens. Okay, number two, hypotheses are using inductive reasoning to formulate a possible explanation for a natural event. Okay, so hypotheses use inductive reasoning to formulate a possible explanation for a natural event. Okay, so predictions and experiments. So deductive reasoning involves if-then logic to then make that prediction, as we're seeing here. Okay, so let's move on to 3B, which we're talking about experimental design. We are going to kind of, in a few slides from now, break down independent versus dependent variable, but just so you can get these filled in. So the experimental variable, the independent variable, is what is being tested. Okay, so that's your fill-in. The responding variable, okay, That is the dependent variable, and it results in data, what is measured, okay? And then of course we have a control. This is the group that's not exposed to the variable. It's not exposed or being tested. All right, we're comparing our data against that control, okay? So let's move on. So you've created your hypothesis, you formulated your prediction, right? And so now it's time to collect your data. Move my little face out of here. Okay. So you're going to want to know, you're going to want to present your data and know that what you've analyzed, right, that you're able to talk about it and that you're able to explain how that evidence is related to either supporting your hypothesis or not supporting it. So we want to ask ourselves these questions. Okay, how can you know if your data supports your hypothesis? When are the numbers significant? How do you know whether to accept or reject your hypothesis? And then what types of hypotheses are there? Okay, so let's quickly go over IV, DV, and then we can kind of break down the two different types of hypotheses. Okay, so I want you to think of the independent variable as the input, right? It's the factor that is being tested. And then of course, our output, what is being measured, that's our dependent variable. So let's apply that then to the two different types of hypotheses. Okay, so I know this is like a wall of words. Just breathe. We're going to kind of go through this. So there are two types of hypotheses. Let's go over research hypothesis first, okay? So research hypothesis, we might assert that a particular independent variable will have an effect on a dependent measure. So let's use the example of exercise and heart rate. So in this example, we would say exercise A is connected to my resting heart rate, okay? So I would say my research hypothesis, it would be that exercise, there is a connection to my resting heart rate, okay? Null hypothesis is stating that there is zero effect due to the independent variable. So essentially, A has no impact on B. So regardless of how much I exercise, it will have no impact on my resting heart rate. So that's how we would see. So for example, the null hypothesis is essentially saying that there's no connection because there's way too many other factors that would be affecting my resting heart rate. I'm not taking into effect the maybe the person's exercise amount, how rigorous the exercise was, what kind of diet does the person have, what kind of genetics does the person have. So nope, I think there is no connection between exercise and this person's resting heart rate. Okay, that would be null hypothesis. Okay. I keep getting my screen get stuck on this. Okay, here we go. So in sort of another visual representation for you, okay? So in the case of a research hypothesis, right, we are saying that the independent variable, the input, my amount of exercise, will have an effect. It does have a connection to my dependent variable, my resting heart rate in this example, right? Okay, but in the null hypothesis version, okay, I'm saying that my independent variable, my amount of exercise, will have absolutely no connection and no correlation to my resting heart rate, the data that I will collect, okay? So let's connect this now to an example so we can try to wrap our head around this idea, okay? Because perhaps you haven't been introduced to statistics yet, so let's kind of break this down. So the investigating question is there a connection between the amount of sleep that you get and your grades? Okay, so if it was a research hypothesis, okay, this first one here would be a research hypothesis. If students get at least 7 hours of sleep every night, then they will earn higher grades, right? So A, input is 7 hours of sleep, leads to B, higher grades, okay? Input is related to output. This one, okay, it's a null hypothesis statement saying there's no connection between the amount of sleep a student gets and their grades. And if we were to test this, because of all of the other factors that are relating to this, how rigorous is the class? How much is the person studying, right? There's all these other variables that would influence it too much. And so there's no connection between the amount of sleep a student would get and the grades that they receive. Okay, so now we need to talk about chance, okay? So chance is always a part of any results, okay? So using statistics, it helps us determine how much of our independent variable was affecting the results and how much was chance affecting the results, okay? And depending on how much that size is, we will either support or reject our hypothesis. Okay, so basically a null hypothesis is saying that everything is due to chance. It's all chance alone. So regardless of the amount of sleep that someone gets, that doesn't matter. It's all about chance. There's no correlation between how much this person's going to get in terms of sleep and the grades they're going to earn in school. Okay, versus the research hypothesis is saying that there is influence from the independent variable. And in fact, that is the reason for and explains the data or the dependent variable. So in this example, right, that if you were writing your research hypothesis, you'd be saying 7 hours of sleep a night does lead to better grades. Okay, so we're just trying to see what role chance has. Is it all chance, so it's the null hypothesis, or is it all independent variable and it's the research hypothesis? So let's use an example of a deck of cards. Okay, we know in a deck of cards there's red cards and there's black cards. There's 4 suites, but right now we're just doing colors. Okay, so if I were to deal you 20 cards from that deck, if it were all up to chance, right? If the rules of probability were exactly followed, right? I would supposed to be getting 10 black cards and 10 red cards, right? So in this scenario, though, the data that we ultimately ended up with was 8 red cards, 12 black. So is that statistically significant enough to reject our null hypothesis that it's all up to chance? Okay, that it should be 50-50. Okay, so let's do the math. Okay, so we're going to start with our researched hypothesis, right? So we have 8 red, this is our observed, and 12 black. Okay, our expected hypothesis was 10 and 10. So we'd fill in 10 and 10 here. So then we solve the differences and we get this. Okay, so expected was 10, so our difference is -2 and 2. Okay, so we're going to break down this a little bit further, but you're essentially going to take the difference, square it, and add both together. So I'm taking -2 squared, that gives me 4, over the expected result was 10. Okay, simple math, that's 0.4. Then again, I take my difference squared, 2 squared is 4, over my expected result, which was 10, I get 0.8. Okay, so I've added up my 2 difference squared over my expected results. So what we're asking ourselves really is 2 things. What does this 0.8 number mean? And will it help us to understand if it was either an okay number, it fit into the range of an accepted deviation, or is it so far away from what it should have been that it is statistically significant, okay, and it's not just due to chance, okay? So this number, what we call this number, this 0.8, it's called the chi-square number, chi square number. So So this is sort of a long form version of what I showed you, right? So we took our observed minus our expected for the red cards and the black cards, and then we added them together. We got 0.8. That's our chi-square number. So now we have a table we're going to compare that 0.8 number to, and we're going to determine whether that number is significant or if we can reject the null hypothesis, and say that it wasn't just chance. Okay, so this critical value that we're going to be looking at on our table, essentially it means that if you are 5% or more of the time, I'm confusing myself as I'm trying to explain this without a whiteboard like I want to. So let's start from the top, okay? So usually the critical value is 5%. This would be your 95% confidence interval. That's the difference from the expected that you obtained that could have occurred due to chance. But if there's a 5% chance or less that you would not get the difference that you did, then that means there's probably something wrong with this deck of cards. So let's look at how it lays out on our degree of freedom table. Okay, so first, how do we figure out which degree of freedom we're using here? So you use the number of variables and you subtract 1. So in this case, we have red and black. Okay, so -1. So red and black, 1, 2, -1. Oh, -1. We have 1 degree of freedom. Okay, so now we need to see where it falls on this table. If it falls anywhere between 5% and lower chances of getting these cards again, these results again, then we're going to reject our hypothesis that says that it's all up to chance. Okay, versus let's look at where our number falls. So we got 0.8. Okay, so 0.8 falls between these two here. So essentially, the next time that we were to play this deck of cards game, right? Do the 20 cards again and see how many were red and how many were black. Between 50% of the time and 25% of the time, we would get the number, the cards that we were dealt, that 0.8 number. Okay. But if we had gotten a huge number, then we would know that there was something wrong with the cards, that the chances of that ever happening again are extremely low. And so we know that it's not just up to chance and that we need to reject our null hypothesis. So this is a larger degree of freedom table, and this would be more similar to something that you'd see on the AP test, okay? So basically, it just gives a little bit more nuance and detail here, but same thing. What degree of freedom are we at? We had 2 red and black, right? We're going to subtract 1, so we're at 1 degree of freedom, and our number was 0.8, so we're going to go across, and we see that 0.8 hits right around here, which is between the probability of 0.46, so 46%, and 1.0, so 107% of the time, we would get that that hand of cards or those color combinations. Okay, so if we had landed over here and our numbers had been the larger values, we would know that it was statistically significant, that there was something going on with this deck of cards that's actually explaining why we got the numbers that we did. Okay, but because 0.8 is in a range that is fair, okay, that it happened between 50, it could have happened between 50 and 30% of the time, we can accept our hypothesis. There's nothing wrong with this deck of cards. So the AP test will provide you with a equation and formula sheet. So and they will provide you the chi-square formula, and it will look like this. Okay, so let's just sort of go through what this equation means so that when you see it, it doesn't intimidate you. Okay, but we've already gone through it, but this is the formula. Okay, so we see, first of all, we know that this here means it's a summation. So we need to add together all of the parts, okay? So we're going to add together all of our observed minus expected squared over our expected. So if we had instead of red and black, it had been the four suites in the deck of cards, we would have had four different pieces to add up here, okay? Because this is a summation, right? And then that this x squared, this is the Greek letter for chi, okay? So basically it's a way for us to analyze our data to see if it falls within the realm of possibilities that we should expect, or is it so far out of that range that we need to consider that something else is influencing this. So we're going to do this example here, okay, to try again to figure out how this chi-square test works, okay? So let's try it again with a null hypothesis, okay? And then we're going to figure it out if it's significant or not. So in this scenario, we're going to be binary, okay? So male, female. We're in this example, we're pretending 50% population is male, 50% female, okay? So currently, 35.2% of chemists in the world are women. Okay, so our null hypothesis would say women are not underrepresented in the field of chemistry. So we are either going to prove that null hypothesis is correct. There's no statistical significance when we do our chi-square test. We're going to prove it, or we're going to do our chi-square test and we're going to disprove this null hypothesis, and we're going to show that actually women are underrepresented in the field of chemistry. Okay, so what I want you to do is pause the video, use the equation, try to test it yourself, and if you're super stuck, if you're super stuck, we're going to move on right now. So if we create a little table here, right? So null hypothesis, women are not underrepresented. So let's look at our observed numbers. So observed, we have 35.2% of chemists are women, meaning 64.8% are male. Okay, if it's expected, if we're matching the rules of binary 50% male, female, right? So then it should be 50% of chemists are female and 50% are male. Okay, so first thing we're going to do is solve the difference. So when you solve the difference, okay, you know that you need to square the difference, right? So you have this table here, difference, you would fill this in. So you can pause the video, fill it in. What's the difference? Then square it. And then finally, you take that difference squared and you divide it by the expected result, which would be 0.5. So, I'm sorry, 50. Don't do decimals here. It'll mess it all up for you. So if we fill it in here, negative 4.8 is our difference here for females, and it's 4.8 for males. Remember, when we square these numbers, the negative will go away. Okay, so if I take 219 and I divide it, so 219, that's our difference squared divided by our expected, which is 50, plus 219 squared divided by 50, we get a chi-square of 8.8. Okay, so now let's ask ourselves, what are the degrees of freedom here? Well, if we remember, we have two components, male and female. So I subtract 1, so I know my degree of freedom is 1. Now I need to check it against my table and see, is this 8.8 number statistically significant and therefore disproving my null hypothesis? Or is it not statistically significant and women are represented in chemistry? So let's take a look. So 8.8, so I'm at 1 degree of freedom. And I'm going across, not seeing it, not seeing it, not seeing it. Okay, it is extremely statistically significant, meaning it's not even on the chart here, meaning that it couldn't even be found 1% of the time. won't be found 5% of the time, 1% of the time. It's fallen off here. So we would absolutely reject our null hypothesis. So if we go back, right? If we go back, this 35.2% of chemists are women, and they're not underrepresented in the field of chemistry. We just proved that it is absolutely disproving this null hypothesis. It is a statistically significant underrepresentation of women in the field of chemistry. Okay. So by doing this, by going through the chi-square test, we're able to explain the quantitative data that we have collected and show and indicate whether it lines up with our hypothesis or it refutes and rejects our hypothesis. And this is where that scientific method and that ongoing process of science comes in, right? If we do the test and our evidence does not support our hypothesis, we need to revise our hypothesis and conduct the experiment again. Okay. And then through the same iteration, right? We have our experimental group comparing to our control group. We analyze our results. Then let's say the second time around, the evidence does support our hypothesis. Then if we repeatedly support the hypothesis that we find, we continue the same test over and over and over again until every single time we're proving this hypothesis. Then we get into the territory of maybe having a scientific theory. Okay. And then once a scientific theory is formulated, then you can build further experiments off of that theory. So, for example, you can conduct experiments about and investigations about evolutionary mechanisms based on your own understanding and knowing about the theory of evolution and how it works. Okay, so it's a generally widely accepted theory, so I can now design further experiments based on that theory. Okay, so we're going to stop it here, and we're going to do more chi-square practice in class.